Good morning, ladies and gentlemen. Happy Mother's Day. I'm still in the kitchen and I still have things set up that are related to pressure and atmospheric pressure in particular. So I'd like to continue talking about how we measure pressures. And this comes up mostly because I have to measure my blood pressure. And this is a blood pressure cuff, and this is a modern pressure gauge, and it's calibrated in millimeters of mercury. Well, a millimeter of mercury is not a unit of pressure. It's proportional to the pressure. You can calculate the pressure from millimeters of mercury, but it's not giving you the actual pressure. Well, the medical profession has settled into using a manometer, which measures, or they use to calculate the blood pressure, but they express it in millimeters of mercury, and that's common and universal and well understood. So let's try to understand what they're talking about. There are all kinds of pressure gauges. You probably have only seen a pressure gauge like this one, and when this reads 0, the actual pressure is already 14.7 pounds per square inch, because this pressure gauge measures the pressure above standard atmospheric pressure. Likewise, this pressure gauge, which is used to measure the pressure of the compression of an engine, it measures the pressure above atmospheric pressure. When you measure the pressure in your tires, these two gauges are again gauges that measure the pressure above atmospheric pressure. That pressure is called gauge pressure as opposed to absolute pressure. Well, millimeters of mercury are not pressures in pounds per square inch. They are simply a length of a column of mercury. And what does that mean? Well, I've specifically taken this stick, I've cut it so that it's 1 square inch on the bottom. So the area of this bottom is 1 square inch, and it's 29.92 inches tall. 29.92 inches is 760 millimeters, less than a meter. The importance of this is if I could somehow take liquid mercury, which I don't have, so we have to imagine, it's very heavy and it's very poisonous, and we have to be very careful with it. But if this was full of mercury, or it was made out of mercury somehow, and I weighed it, if the mercury was, the height of the column of mercury was 29.92 inches tall, it would weigh 14.7 pounds, which is atmospheric pressure. Now, if the mercury was less than that, like this is only 10 inches, then it would weigh less, but we could use the length of the column of mercury to calculate pressures. And that's what I need to do today. One pressure gauge, which is very important to me, is an altimeter. It's a pressure gauge. It measures the pressure in the air and converts it to an altitude. And on the side here, we have a little window where we set the atmospheric pressure that is given to us by the tower or by the controllers. And if we set in the proper atmospheric pressure, it happens to be in inches of mercury, then we will be at the proper altitude. And that's, of course, very important. Okay, so the things that you want to remember are these things. 14.7 pounds per square inch is equivalent to 29.92 inches of mercury in a container like this. That's how much it would weigh. This container, 29.92 inches tall, would weigh 14.7 pounds. Or if it was 760 millimeters, that's the same. It would also weigh 14.7 pounds, and the weight would be equivalent to the actual atmospheric pressure. Well, 14.7 pounds per square inch is over 2,000 pounds per square foot. And the fun demonstration that I want to do today is to show you the significance of pressure. Pressure is not a force. It is a force divided by the area. So if I push down with 10 pounds, the force is 10 pounds per square inch. Now, pressure in a liquid, like air or water, is the same up, down, sideways. It's always the same. It doesn't have a direction associated with it like a force does. And one of the very fascinating things I can do with that is to completely fill this glass with water so that there's not going to be any possibility of an air bubble. Then, believe it or not, I can put this simple piece of paper on top of the glass and invert the glass. I can turn it upside down, and atmospheric pressure is going to hold the water in the glass. Atmospheric pressure is pushing up with 14.7 pounds. The weight of the water is much less than that. In fact, the glass could be almost 30 feet tall, and atmospheric pressure would still hold the piece of paper up against the water. Isn't that fun? Science is so amazing.